Okay, so this is our last lecture for chapter 9, and we're going to talk about more solution concentration units and some things that we can do with solution concentration units. And before I start, there's a last section in lecture chapter 9 too that I skipped over. Let me make sure that we cover it, section 5 on dilutions. This is something we can do with almost all of our concentration units, is we can kind of quickly calculate what new concentration will be if we dilute it. Anybody know what's dilution exactly? Adding water, basically increasing the volume of your total solution. There's a really handy equation that I want you guys to know regarding dilutions. And that's this. I'm going to say C1V1 equals C2V2, where C stands for concentration, so your initial concentration, and V stands for volume. So your initial concentration times your initial volume will be equal to your final concentration times your final volume. Now this should actually make sense, because remember, concentration is always in units of my amount of solute divided by amount of total solution, right? So if I multiply concentration by the volume of my solution, I'm canceling that out essentially, and I'm left with the amount of solute, which never changes in a dilution because I'm not adding more solute. I'm always adding more of the liquid to increase the volume of the solution. So essentially this is saying the amount of solute stays constant. So if I multiply the concentration by the initial volume, that should be equal to my final concentration times my final volume. And this will actually work for almost all of our concentration units, but it'll especially work for molarity, which is where I want to plug it in. So just as a, I think in the lecture notes, I give you M1V1 equals M2V2, so you can look at M as molarity. But molarity is just a unit of concentration. So this is a little bit of a broader applicable formula to use. So if, for instance, I say I have half of a liter of 0.10 molar sodium hydroxide, and I add enough water so that this becomes a 2.5 liter solution, then the question is, what is my final concentration of sodium hydroxide? How would I set this up to solve what my new concentration is going to be? .5 liters. Oh, 2.L liters. That's terrible. Yes, 2.5 liters. Thank you, Candace. Perfect. I'm just going to plug it in there. I'm looking for concentration, so that's going to be C2. So if I solve this for C2, I'm going to find that I get C1V1 over V2 is equal to C2. By the way, I do think it's easier to manipulate all of your equations, including your gas law equations. Manipulate them before you plug your numbers in. It makes your life easier, I promise. So if you do that, then we'll find our C2 is equal to my initial concentration, 0.10 molarity, multiplied by my initial volume, 0.5 liters, divided by my final volume, which is 2.5 liters. And notice if you keep your units there, you'll end up with units of molarity, which works for concentration. So it's really just, what do they call it, a plug and chug. A little bit of algebra here. Oops, multiply that by 0.5, divide that by 2.5. We get a value of 0.02 molar sodium hydroxide solution. Everybody feel pretty good about that? Okay, so if you look at your Chapter 9 in-class activity sheet, this first section is to calculate dilution quantities. So if I start with this volume and this concentration, and I want this concentration, then what's my final volume going to be? Or if I have this initial concentration and this initial volume, and I want this final concentration. No, the question is not what the final volume will be, but how much water I would need to add to make it that final volume. Okay, but both of these use that C1V1 equals C2V2. And I'm going to let you guys do those because I'm pretty sure you guys can do those without a problem. We'll come back to them if we have some extra time, but I want you guys to try those. Okay, next, we've got 2 more units of concentration that you guys need to be aware of. And the first is equivalence, also known as EQ, and often reported as milli equivalents. So that would be a little m for milli, EQ. You guys know what the conversion between 1 equivalent and a milli equivalent would be because that's a metric unit. When would we use equivalents? Anybody ever seen equivalents reported? Chana, I don't know if you're saying K as in like okay, or whether you're saying K as in I've seen milliequivalents reported in concentration of potassium. Yes, okay, excellent. Yeah. Okay, that's exactly, I wasn't sure, I wanted to make sure. Okay, so yes, equivalents are useful when I want to know the concentration of maybe just one ion. For instance, if I want to know the level of potassium in your blood, or maybe I want to know the level of iron in your blood, or I want to know the level of chloride in your blood, right? When I say in your blood, because this is where you often see it, is in blood testing. And as future healthcare workers, or maybe current healthcare workers, you will see and do and be exposed to a lot of this. So it's important that you know what this means. So the reason we use equivalents are because blood and cells have really complex mixtures of ions. It's not as clear and as easy as saying, hey, I'm looking at a solution of sodium hydroxide, or a solution of potassium chloride, or a solution of iron nitrate, okay, iron 2 nitrate, right? It's not just one thing in there. In your blood, you've got all sorts of stuff. You've got sodium running around. You've got potassium running around. Oh, hello, potassium running around. Just K? No A. You have calcium running around. You have iron running around, usually bound to something else, but it's running around. You have chloride running around. You have carbonate running around. You have hydrogen carbonate running around. You have phosphate running around, probably hydrogen phosphate, etc. You have lots of ions running around. Yeah, sorry, reload, Robin, see if that helps. So it's not like I can measure the amount of sodium carbonate in the blood because sodium's not bound to carbonate. All of these are ions, and as we know, ions are dissociated in solution, so they're not even like, they're not stuck together, they're not associated with one another, they're just floating around independently. So it makes no sense to try to measure the amount of calcium chloride or the amount of calcium carbonate when really what you want to know, what you care about is, for instance, How much calcium does this person have running around in their blood? How much iron do they have? Because we want to know if they're anemic. How much potassium do they have? Because we know that this person has kidney disease and that might be dangerous, all right? How much hydrogen carbonate? Because we need to know about adjusting the pH here. So we want to know just one thing. That's where we look at equivalence. So I'm not looking at a package deal like the concentration of a molecule or a compound, but just then a single ion in solution. All right. So here's the equation that you need to know. One equivalent of anything is going to be the molar mass of that thing divided by the charge of that thing. And essentially that gives us what we call equivalence. And then in order to call this concentration, we're going to report something like equivalence in a liter or milliequivalence in a liter or in a milliliter, for instance. But this is just a way of representing the amount of solute by using the equivalence. So for instance, then, one equivalent of chloride ion is the molar mass of chlorine, which is 35.45 grams, divided by the charge, which is 1. So one equivalent of chloride is 35.45 grams. Okay. If we did this with iron 2+, we would find that one equivalent of iron 2+ is the mass of iron, which is 55 of wait. Yeah, 58.85 grams divided by 2. So in that case then, one equivalent of iron 2+, oh my, hang on, back up, 58.85 divided by 2 gives us a mass of 29.43 grams of iron 2+. That was Cl-. Not yet, no. We're not quite to osmolarity, because osmolarity is still looking at all of the species in solution, whereas we're just concentrating on one thing. If that makes sense. Yeah, just jumping ahead. It's okay. Okay, so that's how you calculate equivalence. And then to use this in terms of concentration units, they're going to divide this by an amount of solution. And you guys know how to do that with dimensional analysis. So let's just do a couple examples like this in your in-class activity sheet. And so long as you can remember the formula, this formula, equivalent is the molar mass divided by the charge. And then your units are in grams, because that's the mass, which comes from grams. You should be good. So here's a good particular question. Normal blood, so like a healthy sample of blood, is going to contain 3 milliequivalents of magnesium 2+ in a liter. So 3 milliequivalents Mg2+ in 1 liter of blood. Okay, so then the next question is, how many milligrams of magnesium 2+ are present in 100 milliliters of blood? And from here on out, it's literally just dimensional analysis, but you will need to know what an equivalent is so you can convert between equivalents and grams. So according to our formula, one equivalent of magnesium 2+ is going to be what? Molar mass over the charge. So my molar mass of magnesium is, oh, I don't have a periodic table handy. Let's see. There we go. There's one. 24.31 grams. Okay. So 24, oh, excellent. magnesium and divided by the charge, which then is 2. So 1 equivalent of magnesium 2 plus is going to be what? (12.155 grams of magnesium 2 plus. Okay, so this is a conversion factor. All right, so we start with milliequivalents per liter, and we want to know how many milligrams are in 100 milliliters of blood. This is a liter of blood. Okay, what should we do? Okay, there's more than one thing that we will need to do, and they're both correct. Exactly, or both. Okay, and we can kind of go from multiple directions here, all right? We will at some point, because this is milliliters of blood and this is liters of blood, we're either going to need to convert the liters of blood to milliliters or the milliliters of blood to liters so that we can use them to cancel each other out. So perfect, Candace. This is milliequivalents and this is equivalents, so we are going to need to convert from milliequivalents to equivalents so we can use this to cancel out as well. All right, so both of what you guys said was exactly right. Let's start, Joyce said it first, to convert to equivalents. So we'll go from milliequivalents to equivalents. How are we going to do that? Put milliequivalents on the bottom. Okay, so how many milliequivalents are in 1 equivalent? 1,000, because that's what milli. Excellent. Okay. So now we're at equivalents. Now what should we do? Perfect. I'm going to take this conversion factor that I came up with and just plug it in. 12.155 grams of magnesium in every 1 equivalent of magnesium. My equivalents cancel and I'm left with grams. Excellent. Oh, I'm not done. I still have 2 things that I need to do. You guys tell me what to do. 1,000 milligrams in a gram, and I have to do that because I asked for milligrams. So, excellent. That's going to give me milligrams. But there's still one thing not canceled out. I've brought this down to the number of milligrams of magnesium in a liter of blood. But I want to know how many milligrams are in 100 milliliters of blood. Okay. So, Candace, you're telling me I need to convert from liters to milliliters. 1 liter is 1,000 milliliters. And then, because I have 100 milliliters, I'm going to put this out here. Milliliters cancel. By the way, I could have set these things up over on the right-hand side, but I was running out of space. Also, it's nice to start expanding my dimensional analysis this direction because then that puts these next to one another so I can see more clearly how they cancel. But it's not at all necessary. Order of operations says that you multiply and divide same order of operations. So I could have put liters to milliliters and then 100 milliliters out here. But that's just fine. Look at that. That's fancy. We just got fancy with dimensional analysis. It does feel comfortable to put it next to what you're trying to cancel out, doesn't it? Okay. Now, all right. We've got this set up. All of our units cancel out. Dimensions check out. So that was the point of dimensional analysis. So now I can say 100 milliliters divided by 1,000 milliliters in a liter, multiplied by 3 milliequivalents in a liter, divide that by 1,000 milliequivalents in 1 equivalent, multiply that by 12.155 grams in 1 equivalent, and multiply that by 1,000 milligrams in a gram, and I should get that 100 milliliters of blood contains 3.65 milligrams of magnesium. That was kind of a mean problem. That was a lot of extra conversions. I'm not going to have this many steps on an exam, I promise. But it really is, it's just all dimensional analysis, just getting fancy with dimensional analysis. And really, 3 of your conversions were just knowing what milli means and putting those in the right place. So that's not a big deal. You guys can do this. I know you can. I know you can. All right, let's talk about osmolarity. Because we want to make sure that we cover all of this, and this is where it starts getting fun. Well, I mean, it's already fun, right? Where might we see units of osmolarity? I first saw osmolarity as units of the IV solution. What's osmolite? Is that an IV solution or is that something else? Yeah, exactly. An IV solution. Excellent. Okay. And it's important in that context because of something known as osmotic pressure or osmosis. Osmosis is a naturally occurring process where if you have what they call a semi-permeable membrane, so here in the middle is a semi-permeable membrane. Semi-permeable means some things can cross but not others. So let's say I've got a solution here on both sides, and water can cross the membrane, can go back and forth, but ions cannot because water is smaller and not charged. Okay, but ions cannot. If I set up the solution and I make it something really concentrated on one side, like lots of salt, and then a really weak concentration on this side, okay, then naturally occurring process, water will cross the barrier. I mean, it's always going back and forth, but it will eventually net gain move to the left such that it will try to equalize the concentration between the sodium chloride on both sides. So after some time, then your semi-permeable membrane here will have a higher concentration of water on this side than this side, because that will give it the same relative concentration, insofar as it's possible, of ions. Okay, that's exactly what it is. It's a concentration gradient. The gradient based on the fact that there's a difference in concentration across the semi-permeable membrane. Okay, and the concentration, the difference in concentration doesn't have to do so much with how many sodium ions and how many chloride ions there are, but how many things there are dissolved. So for instance, your cells then maintain, if here's your little cell, maintain a concentration gradient between sodium and potassium, where they have maybe more sodium ions on one side and more potassium ions on the other side. but they do it such that the concentration of positive ions on both sides is the same. And so it doesn't feel that pressure from the osmotic pressure because the number of ions is the same, even though they're different ions. Okay. But if your overall concentration of ions is different, then there's a literal pressure, we call it osmotic pressure, that pushes water, or we can say pulls water across so that it will establish the same concentration of ions on both sides. Okay. Your cells are semi-permeable membrane. They're subject to osmosis. And so we end up with a potential problem when somebody comes in to the hospital and they are dehydrated and they need more water in their blood, in their body, because they're dehydrated. Or maybe you guys want to set up an IV drip so that you can pump drugs in through it, like anesthesia. And you need to make sure that the concentration of solution that you're dripping in your IV bag and going into the bloodstream is similar to the concentration of ions that naturally occurs in the bloodstream and in the blood cells. Because what would happen if your IV bag was more concentrated? What would happen? Pumping in a whole bunch of extra ions here. Water is going to come from your cells out into your bloodstream to compensate for those extra ions to reestablish the same relative concentrations. And so what happens to your blood cells? If we have a strong concentration, well, if it's dumping water outside of the cell, then they're going to shrivel, right? And die. Whereas if we have a weak IV solution and we dump this into the bloodstream, so we're just putting in water and we're not putting in ions, okay, extra water, that's going to take the ions that are in the bloodstream and make them more dilute. And so since you kind of naturally had this, what was there previously as shown in red, then we're going to say, oh, we want to reestablish the right relative concentration. So then our cells are going to absorb a bunch of water to get bigger so that the relative concentrations inside and outside the cells are the same. And in this case, your cells, red blood cells, will swell and burst and die. Whereas this case, they shrivel and die, okay? So it's important to have an IV bag then that is essentially giving you the right concentration of ions so that your red blood cells don't shrivel or burst and die, because that would be a problem, right? I hope everybody in this class could understand that that would be a problem. A big problem, right? That patient would die, could die if you didn't catch it fast enough, okay? Big problem. All right, so even just something as simple as selecting a solution to administer by IV could be deadly if you chose the wrong concentration of solution, okay? All right, so you might have heard the terms a hypertonic or hypotonic solution. Hypertonic is a higher concentration, so that would be this case. I'm not going to test you on this, but I'm just putting this out here because these are nursing words that you might have heard. This would be a hypotonic because it would be lower concentration. What you really want is the concentration which is the same as your blood and your cell cytosol. So that would be isotonic or the same. So many IV bags are just like shipped and stored and they're already at the right concentration. Some of them, particularly if you worked in a pharmacy, might come extra concentrated and you're supposed to dilute them before you administer them to the patient. So there's less shipping involved. And you have to make sure that you do dilute them. Otherwise, there's going to be a big problem, if that makes sense. Okay, so that's the theory behind osmosis and osmotic pressure and osmolarity. Let's talk about what osmolarity is as a set of concentration units, because that's what we're going to be calculating on an exam. Osmosis has to do with the presence of ions and not the identity of what the ions are necessarily. Okay? For instance, your concentration gradient that's normal in a cell might have sodium on one side and potassium on the other side. And it doesn't matter that one side has all the potassium and one side has all the sodium because you've got the same number of positive charges on either side. Okay, so osmolarity is a unit of concentration where we're looking at molarity, that's where it comes from, is moles per liter, right? So osmolarity is the molarity of all ions divided by liters of solution. And the quick and easy way to calculate this, if you just got one thing in solution, is to calculate the molarity of that solution, which is the number, the moles of that species, and then multiply by the molarity by the number of ions that dissociate in solution. I shouldn't say ions, it should be all species, right? But we have to remember that ionic compounds dissociate, so they're going to form individual ions, so they're going to form multiple species. All right, I'm going to say species. So for instance, if I had a 0.5 molar solution of sodium chloride, how many species are going to be dissolved in my solution? I mean, is this just one thing or is it going to dissociate? What do you know about sodium chloride? Yeah, it's two things because it's an ionic compound and you know that ionic compounds dissociate. So really I have 0.5 molar sodium and 0.5 molar chloride running around. So this translates into a 1 osmolarity solution. You can compare this to a 0.5 molar solution of glucose. How many things do I have here? Does this dissociate? Is this one species? Is it going to be 20 species? What is that? It's one. It's glucose. Glucose is a covalent compound. Covalent compounds do not dissociate. And so, since it's just one thing, this ends up translating to 0.5 osmol, right? So I took my molarity and multiplied it by the number of things that are going to be in solution to get my osmolarity. You guys following me here? I need at least 2 people to say yes, and then we'll go over to our in-class activity sheet. Okay. And if you're not following, I hope you're asking questions. Okay, so here, calculate the osmolarity. Remember, osmolarity is molarity first, and then multiply it by the number of species second. You guys already know how to calculate molarity, because this instant you hear the word molarity, you're going to go, what? What will you think? Moles per liter. Perfect. And then the Oz part is going to say how many species we have. Okay, so for instance here, let's do this particular problem. Molarity is moles per liter. Here's moles and here's liter. So you know how to set this up. Moles NH4Cl divided by 0.4 liters. That gets me molarity. And then to get to osmolarity, I'm going to multiply it by the number of things. Is this ionic or covalent? How many things are going to be in that solution? Two. That's ammonium chloride, ionic compound between the ammonium ion and the chloride ion. So we're going to multiply that by 2 to get osmolarity. So 0.0345 divided by 0.4 times 2. And I get 8.1725 osmol concentration. Excellent. Okay. That's what sections 3 and 4 are talking about, osmolarity. Again, you guys know what molarity is, and at this point it's just a matter of recognizing, is that ionic or covalent? How many ions will I get if it's ionic? Counting those up and multiplying them in. Okay, osmolarity also affects, in addition to osmotic pressure, it affects physical properties of a solution like melting point and boiling point. These are called colligative properties, or properties of a solution, which will change slightly depending on concentration of the ions or the species in solution. And this is a formula that you'll see using constants that I would give you because it's specific to each solvent. So K sub F is the freezing point depression value. K sub B is the boiling point elevation value, because we find that for all solutions, when we add solvent, my freezing point always goes down. So we call that freezing point depression. Oh, and my boiling point will always go up. Okay. This is why, for instance, we put salt on the roads when it gets icy, because then it lowers the freezing point of the water. It allows that ice to melt, and then that melted ice can flow off of the roads and they won't be icy and slick anymore. But these are given in degrees Celsius per, let's see, here we go. Boiling, the KB here then is 0.51 degrees Celsius per mole of solute, and that's not like NaCl, but individual species. So you could call that osmolarity essentially, per osmol. And so both of these are using the KB. So I'll do this problem with you guys. Actually, I'll do this problem because this is a covalent compound. So molarity is the same as the osmolarity. This takes an extra step because it's an ionic compound. So my boiling point will increase by basically 0.5 degree Celsius for the osmolarity. Then, okay, 250 grams sodium chloride. I need molarity, so I need to go to moles. So 22.98 plus 35.45, molar mass of 58.43 grams per mole. Not that I ever expect you to memorize these, I just use them so often that I know what they are. And then it says 2 liters of solution. So if I do that, I've got moles per liter, which is molarity. And then what else do I need to do? I got to molarity, but I need osmolarity. So what do I need to do if I'm talking about sodium chloride to go from molarity to osmolarity. Times by 2, because there will be 2 sets of ions in solution. So multiply by 2. So 2 ions for every 1 sodium chloride. You could look at that like. Okay. So that gives me 2 times 250 divided by 58.43 divided by 2. Osmolarity of 4.28. And if I know my boiling point raises by 0.51 degrees Celsius for every 1 osmol, I'm just going to multiply that through dimensional analysis. You guys can do this. I find my boiling point increases by 2.18 degrees Celsius. Now the question isn't what's the change, but what the final boiling point is. So there's one other, yes, exactly, Candace. You have to add 100. Why did you add 100? This is a piece of information that you guys should just know. 100 degrees Celsius is the original boiling point of water, boiling point of pure water. So when we say boiling point elevation, we're saying this is how much higher it will boil than normal. Okay, so if it normally boils at 100 and I've raised it by 2.18 degrees Celsius, now it's going to boil at 102.18 degrees Celsius. Excellent. You guys are professionals. So my boiling point difference here. Hang on a second. This is not a formula. I'm just saying that that's what the QB was. 2.18 degrees Celsius. Add that to 100, and I get a new boiling point of 102.18 degrees Celsius. You guys can do this. I believe in you. Okay. We've got 1 minute left. I want to talk to you guys about section 6. Section 6 is nothing new. We've covered everything that is in our lecture notes for chapter 9. Okay. What section 6 does do is take information that is new for this chapter, like concentration units of molarity, and apply it to what we've already done in chapter 6 with mole to mole ratios, mass to mole ratios, etc. Okay. So for instance, if I give you an equation and say I start with 5.5 grams of this, and I know I'm using 16 molarity solution of this, the question then is what volume or how many milliliters, how many liters of this solution is going to react with that. Okay, so this is your conversions roadmap with this added part where you can convert between moles of A and moles of B, for instance. You can also convert between moles of any of these things to concentration of B, brackets means concentration, if I have the volume, right? So I can go from grams of potassium hydroxide to moles of potassium hydroxide using molar mass. I can go from moles of potassium hydroxide to moles of HNO3 using my coefficients of the balanced equation, which I haven't necessarily balanced yet. And then if I know moles and I know molarity, which is moles per liter, I can use those two together to calculate liters. It's all dimensional analysis, okay? So there's nothing new in this section. I'm just forcing you to put together something that we've already done with gram to mole and mole to mole ratios from chapter 6 with something that we learned in this chapter, which was solution concentration units, but it's all dimensional analysis. And I have full faith that you guys can do this. There will probably be a question like this on a test, maybe just one. That's like your capstone question for the test. Can we put this together and apply it on the exam? So that is it. And I would be happy to do one of these with you in class on Wednesday right before we take the test too. But yeah, that's what this is. The first two, we're looking at concentration units. This last one gets even fancier because I give you volume and ask for concentration, and I give you then volume of a gas here. So you're going to have to use gas laws to get back to moles for H2S, and then use that moles of H2S to calculate moles of HNO3, and use that to calculate your concentration. You guys can do this. You have all the tools. It's just putting it together in a different way, and it should be fun. Look at it like a puzzle. It's a puzzle.